Okay, it would have been a gorgeous video, but we skipped that. So the idea of Kinematica is basically we wanted it to be precise. So you can do things like precise environment contexts, you can vault over and cover, you can precisely define where you want your character to make contact with the environment. We wanted it to be responsiveness, we wanted it to be responsive. Of course, you want to be able to use it for player-controlled characters, so if you make fast joypad movements, your character needs to feel responsive. We wanted it to always have a high quality. We wanted to be able that you can have a lot of variation in the animations. So the system should never merge poses together or in any way modify the data that you as an animator put in. And of course, it should be at least as fast as any traditional animation system. So you should not have any penalty when you would use Kinematica. So since apparently videos don't work, I just sort of like imagine this is a video of Hitman Absolution. And as you... Yeah, I can't do anything about it. I'm really sorry. Huh? The problem is I have a lot of videos, so that's the only problem. But imagine that Hitman would go through that door, right, and then you see this massive crowd over there, right? So so we wrote the engine for Hitman Absolution from scratch, and there was nothing. At some point, we had to create a crowd system, and we used traditional animation systems like anybody else, and we thought, hey, let's try it out. We only want to have 1,000 characters running in the simulation. What can go wrong? And then we found out that that does not really work. So then we started brainstorming, and I sort of came up with the idea, hey, let's just skip all this animation graph stuff and just somehow figure out which animation clips would make sense for characters to animate, right? So the AI just says, I want the character to go here, and it was a very, very simple hill climbing cost function thing. It was a very, very tiny idea, but this is where the idea started. And I made games all my life long. I mean, that was the first game that I ever published. That was on a C64, even though the screenshot says Amiga. I was in, I think, 91. And worked on many, many games over the... since then, worked at Ubisoft over the last couple of years before I joined Unity, contributed to all those games. And this is a recurring theme. We have a lot of pain points when we want to animate characters. It always requires a lot of time and effort. So thankfully this is not a video, but I have that running here. So, and I need to move that over. So, of course you know all of that. You all know this. This little example tutorial here. That's the third-person package. It's not meant to be high quality. It's meant to, of course, get you guys going. But when I look at it, something is really immediately obvious to me. It looks, the transitions between different movements all happen as you press your button, right? It's the code behind the demo is intentionally kept really, really simple to sort of like make it as small as possible. But when I look at it, of course, you can immediately see that you just straight blend from one animation to the next, and there is no transition in between. And of course, you would then just add transitions to it. You need to add animation. You need an animation state and transition into that and out of that, and all of that needs to happen manually. But there's also another important point when you think about it. Why would we want to add those transitions? And that brings me to the topic of anticipation. That will be really awkward now without videos, that part, but well. So there is this book by some famous Disney animators, Ollie Johnston and Frank Thomas, and they wrote this book, The Illusion of Life, Disney Animation. And they basically tried to collect a number of ideas for how to make animations look good. And it's a really gorgeous book, and there are a couple of YouTube videos that sort of like summarize all these ideas. It's really interesting to watch. But today I just wanted to talk about anticipation and why that is important in our context. Anticipation is something that pretty much is part of each and every movement. So if videos would work, this would be baseball. He would sort of like, the baseball would come in and he would sort of like hit the baseball, and you can see his nice backswing, right? And that part of the entire action is the anticipation. And it is so important because it tells the body mechanic of an action. And you immediately see that something like that is missing, if it is missing. So this is some parkour moves, and it's the anticipation is this coiling up and getting ready for your jump. And if you would, or you have a golfer who would sort of like hit that ball with a nice backswing, or pitcher. And in that video, I removed the anticipation, and it looks really awkward. Skip over the videos. So anticipation is very, very important for a movement to look believable and realistic. And it's mostly a term that is coined by animators. From a more technical point of view, it basically means because we want to sort of like replicate the real world, since a person can't instantaneously on the spot turn around, we want to sort of like see that that character preserves inertia and momentum. And that in turn gives us a sense of weight. If something turns on the dime and goes from left to right in an instant, it appears as if it has no weight. And my main point with all of this is I see so many games where it basically looks like in that third person example where the guy is just, his root transforms just procedurally turned around on the spot. And to me, I always think, why? I mean, we can just sort of like have a really nice animation, and of course we don't want to lose the responsiveness. We can still modify the root transform such that it feels responsive, but we can do much, much better than completely ignoring it. And on this entire principle is the core idea, how the API and the idea around Kinematica. So in that video, so in that still image, the mocap actor runs towards the camera, and he does this slalom movement. And in that video / still image, I annotated, so he would sort of like basically run this little slalom S-curve. And I highlighted where his root would be. So in case somebody doesn't know what the root transform is, it's basically you take the center of mass of your character, you project it onto the ground, or you have some other rule for how to generate this, or you have an animator creating it. But it's basically a position and an orientation where you're that your character, the skeleton, is relative to. So that would be, I mean, I drew this by hand, but it roughly corresponds to the actual root transform. So it would look like this. And if you now take a still image, and then one second. And then removes part of this trajectory, and you only leave a little bit in front, ahead of the character, and behind the character. Everything else you just remove. Then, and you look at this, then I could ask, hey, can you guess the next pose? and you could give me an answer, right? It's pretty easy to understand how the next pose would look like with that, just with this information. If I now, I don't know if you saw that, but I'm bending the trajectory a tiny little bit, so it goes a little bit straight. And if I now say, hey, can you guess the next pose? You could also give me an answer. It would, we could reasonably understand how the next pose would look like if we have just this information where we want the character coming from a slight little turn, or sharp turn, and then we ask him to go forward. And based on that principle, that's the basic idea behind Kinematica. The whole thing is based around calculate the next pose given a desired trajectory. Let's dive a little bit into how that works. Luckily, I have that as a demo. Ugh. So this is, 1 second. So this is one of the animations out of the motion library that we used in the demo. And I only show a debug drawing of the skeleton and the trajectory of the entire movement. And in that particular case, with many of those longer animations, but basically we ask the actor, hey, just run in a circle at different speeds. And on the ground, those pink lines, that is the trajectory of the entire however many thousand frames that we have here. I can now do the same thing that I did in the actual video footage that I showed on the previous slide, and I can just say, hey, snip out a little bit from this trajectory and only show me the next tiny little piece. That is now 1 second worth of trajectory, but the pose stays the same. I didn't do much, I just sort of like don't draw all the trajectory. Now I can say, well, what if I transform all of that into the origin? I can still play the animation, of course, it's just a different visualization, it's the same data, it's just looking at the data in a slightly different way. The character is now always at the origin, and that little line on the ground tells me where he would move next. So I can reason about the pose that the character is in and his movement. And this is, of course, a trivial example. This applies to any kind of movement. It could be a melee fighting movement. It could be crazy parkour movements. The idea is the same. Oops. So Kinematica takes all the animations that you put inside and stores them in one giant library. And all the poses are kept in chronological order. So on that previous image with the skeleton and the line on the ground, me drawing the line, I can just walk across this big giant matrix. So I sample the matrix at one column. That is one pose. I can draw the skeleton, and then I can look into the future or look into the past by just stepping across a row of that matrix and only sample the root transform. So with that little trick, you can look into the future or look into the past. So the problem is now, reduced to, hey, we have a current pose. That's the one that we are rendering the character at or with. And we know how that trajectory of that character evolves over time. That's already contained in the animations. And we know that is now the gameplay input side of things. We know how we want the character to move, actually. And if ever the actual trajectory of the animation deviates too much from what we want, then we simply find a little piece that matches what we want. And that's the whole trick. Can I please? In a sense, it's a multi-objective constraint optimization problem. Multi-objective because the objective is how we want to move our character over time. And the constraint is the pose that we are in. We will most likely in our big giant animation library find a little piece of trajectory that matches what we want, but the associated pose does not match. So we need to satisfy both requests. And this is, okay, let's skip that because it's a video and it's difficult to explain without. So that video would have explained that picture a little bit, but basically the blue skeleton is, let's say, the pose I'm in right now, and there is a little offset pose. It's another blue skeleton that is a little bit ahead of the other blue skeleton. So there are two blue skeletons that are offset by a little bit. And those are two poses that come right next to each other in the animation. And there is on the, I think it's the left ankle, there is a little red line that connects the ankles of the two blue poses. And that indicates the velocity of that pose, of that joint. And there's only the linear velocity. And the yellow skeleton is some random candidate pose that I want to know, hey, does that match? Does it not match? Can we use that as a possible continuation? And we use several characteristics. So for example, obviously the joint distance needs to be rather small. So we don't want that one joint, when we sort of like leave one animation stream and transition into a different one, that this is 1 meter apart. We use linear and angular speed, so how long are those lines? We care about the joint direction. So for example, if we, let's skip this. We only also use a subset of joints. So for the demo that you've seen, we only use both feet and the neck. So we only use 3 joints to determine whether or not poses are similar. And when I said we don't want joints, for example, to be too distant from each other, we use a linear function to determine that distance at runtime. So essentially, I'm saying the faster my character moves or the faster my joint moves, so let's say I'm punching right now, then I can allow for a larger deviation. You will not notice that the next pose I'm transitioning into is 0.5 meter away. It does not matter. You will not notice. But if I'm moving very, very slow, you will notice if the transition covers too great of a distance. So let's get to something hopefully a little bit more interesting. Let's look at how do we all set this up in Unity and how does it work. So this is basically the demo that you saw yesterday, hopefully. And this is the character. I select the character over here. And then you notice this builder component. This API or this This is, of course, not the final user interface. We're currently figuring out how we sort of like package all of this nicely. So the way it works right now, I add a component and I add this component is supposed to generate the asset, the binary asset that the actual system that Kinematica is using. So here you can select or decide about how poses compare, which, for example, here I can define which joints we are comparing and some thresholds and so on and so forth. And down here is the animation library itself. So basically you can add or remove animations at will, and then I can build this asset. It takes like 30 seconds here to rebuild everything, and then you can try it out. So you can very, very easily and fast add, remove animations, and try out, change little parameters. So this part is the asset building part. As I said, that UI will change, but the basic idea will stay the same. So down here, let's collapse this for a second. So down here is that we already enter the gameplay portion of the system. So this part is already something you would write to animate your character. You consume the asset that we built with that previous component, and we basically reference the target character. What happens inside is now completely up to you. For this demo, I wanted to sort of like handle traversal or parkour moves separate from regular locomotion. So I divided that into two other components, and we look at them briefly. But all of these decisions for how you want to have this to work is how you would anyway have to create the logic for your character. When do you want him to jump? When do you want him to climb on something? Is he currently holding on to a wall, and is he climbing? All of this, that is part of the game logic. The only thing that is no longer present is a representation on the animation side. This is just me making a demo, deciding about how do I want my character to move. Oh God, I'm so blind. One second. So behind the scenes, the system uses the new playable graph system and an animation job system. So this node here to the right, that is Kinematica running, synthesizing every frame in new pose based on what we'll look at this in a second. And those other nodes here, they are all procedural animations running on that character. So this character has like 2,000 animated joints. The base skeleton has like 50 animation joints, and we have a bunch of jobs running on the animation job system, all running in parallel on separate threads behind the scenes, animating the character. Okay, so that was just sort of like a brief overview of how does how did I set up this demo, and how did I sort of like architect the interfacing with Kinematica. was the wrong one. So let's look at the locomotion ability. How does that part work? Don't crash on me. So here I made a tiny little example scene to get the basic idea across. So as I... Oh yeah, okay, of course. Yeah. So I made a tiny little toy project. So as I move gamepad, I move my little transform around. And when I say transform, I mean that little cross right in the center of that little snake, right? So that the blue line indicates the forward direction of my character, and the head of that little tail indicates how I think, how I want my character to move in the future, and everything that is past my little transform, that little cross, is where my character has been in the past. And I can show that code very, very quickly, but it's super trivial. Basically, it's a tiny little mental shift from how we would usually do this, right? I mean, usually you have your... zoom in a little bit, and I think it's a little bit difficult to see. So usually you would have, of course, exactly the same transform for your character, and you would just rotate the guy around regardless of how he moved in the past or how he moves into the future or how we want him to move in the future. The only difference here really is we take the current transform of the character and then we read a desired velocity from joypad and then interpolate between the current velocity that we are traveling with right now and at which velocity we want to travel in the future, like 1 second into the future, and interpolate these two. And that gives us this movement. And that is the basic fundamental building block. Exactly this information we pass to Kinematica, and out we get a pose. That's all you have to do. And you can... oh, I forgot to show that part. That's no, that was not us. I already was asked yesterday, hey, why is that character so slow? Why does it appear so slow? Well, I can... So here I have my little... I'll show you the code in a second, but I made it such that you can see this little snake, right? I made here little sliders, and now it's instantaneous. And if I feed this into Kinematica, I get a very snappy pose. I get much more rapid movement. Of course, you lose a little bit quality, right? Because the character cannot turn on a dime, but it's up to you. This is a tiny little toy example, but this is all you have to do to animate your character. Oops. Okay. Let's very briefly look at that one. So I made a little struct. I called it trajectory. I said at the very top, time horizon. That's my prediction. That is 1 second in this example. I want it to be independent of the game frame rate. So I say, well, I want it to be, for example, sampled at 30 frames per second. So my trajectory would have 60 samples because it is 30 samples in the future and 30 samples in the past. So it's just an array. At the very bottom, you can see affine transform array root transforms. That is an array with 60 transforms, and that's all this thing really does. It's a super simple wrapper. Then I initialize that guy and say, hey, 1 second, 30 FPS, and hey, start where my transform, where my game object is right now. And then in my update loop, I predict, I mutate this array. This is what I call predict. That's what you have to do. And then you call into Kinematica, and Kinematica spits out a pose. And the rest is debug draw for this little example here. That's how you would read the stick input and calculate, turn this into, make it camera relative and turn this into a velocity. And this is one example. This is how I decided to sort of like make that little trajectory. You can do it differently. It's based on a little exponential curve. Basically, that for loop right in the middle here reads out one transform at a time. And as we sort of like step from the time where we are right now, as we progress through this 1 second worth of prediction, I calculate a little weight that I call here percentage. And that starts at 0 and it ends at 1. I turn that, I have these little sliders that turn that into an exponential curve. And I basically blend between the current trajectory, i.e. the line on the ground, and what I want to do. I just blend those two together, and this blend weight changes gradually from 0 to 1 as we step into the future. This is exactly the same demo I ran on the machine yesterday, and here on the ground you see the trajectory. It is literally exactly the same code that runs here that you just saw here on the slide, and you can see that it also includes obstacles here. I don't think I have time to go over how I added the parkour moves. But it's basically the same idea. All you have to do is supply a trajectory, and in the case of parkour, contact points, and Kinematica produces a pose. Very, very, very briefly look at collision detection. One second. No, that's the wrong one. Okay, I just explain it. So this line that indicates where we want our character to move in the future. I showed you the code for how to translate your desired velocity into a path that is an estimate for how we think our character would move. Well, what if that path runs right into a collision, into a wall? So, well, just make it not happen. Avoid the wall. You know, you are already, in that example, I'm way ahead of that obstacle that I would run into. We now estimate, or we calculate where we want our character to be. I just do a sweep move with my cylinder, detect that collision ahead of time, and then bend my path. And of course, I communicate that back into my trajectory by bending it around that obstacle. And that is a debug visualization that shows you how that sweep move, that cylinder sweep move looks like. It just goes around the corner, and what you get out of that is a nice little, I go around my obstacle. Or if that is a flat wall, I detect this a second ahead of time before I slam into the wall, and you get a nice little stop. And the character will not just sort of like run into the wall on the ground. And it comes naturally. So I think I'm out of time. well, if you guys want, we can talk about parkour, but let me briefly explain that. So this was sort of like a tiny little sneak preview. There's more to come. So I definitely want to show melee combat and climbing and physically based character simulation. So I'm currently working on the demo for that we show at SIGGRAPH, and we show another demo in LA at Unite LA, where we show what I just said. So melee combat, climbing, full body AK, all of this combined into this. This was just the very first sneak preview where I thought it would be nice to show parkour moves. And right now we're also busy working on tools, like for example, it's very, very, well, it would be really cool if you can just play your character and then you pause the game and you have a little time slider and scrub back in time and can inspect, why did it choose to do this? Or, here at that point I supplied a wrong trajectory. I want you guys, of course, to have an easy time doing that, so we're working on these kinds of tools. And they, of course, will be ready before we release this. Thanks very much. That's it.